All right. Let's reconvene. Let me make, before I turn over the mic to Squire, let me make one quick announcement. I have been asked by several of you about these open slots for the practicals. So the way we have done this in the past is you can come and see whether you can, there is still an open slot. I believe the last the document that is uploaded right now is accurate. I think your schedules that you have are a good starting point for this. What we have done in the past is people, rather than really signing up and creating new schedules, people walk around to the respective station and ask whether there is still the open spot. Some of the methods could accommodate a seventh person. Some methods we don't want that, like high resolution mass spec. We don't want crowding around expensive equipment. But yeah, so that's where things are mostly on a self-regulating basis. So just this first afternoon session, it's pretty much booked. There is officially an open seat on paramagnetic NMR and so on and so forth. But you can come see me afterwards. You can take a look at this. And, I think just talk to the people who run the show, and we'll take it from there. And now I turn over the mic to Squire, who introduces the next speaker.
Hi, my name is Squire Booker. I'm a professor here at Penn State. And I'm super excited to welcome Dr. Sean Elliott to give our next lecture on protein electrochemistry. I've known Sean for quite some time. I knew of him when he was an undergraduate at Amherst working with one of my ex-colleagues, Joan Broderick, and then he moved to Caltech where he worked with Sonny Chan, and then on to Fraser Armstrong's lab in the UK where he learned this technique of protein electrochemistry. And so in this technique, what he does is basically he applies the protein as a film to a type of electrodes like graphite or something like that. And he can look at potentials of cofactors in enzymes or other types of biomolecules without the need for mediators or other small molecule interceptors. Sean has taken this technique to a higher level where he's able to actually look at enzyme turnover using electrochemistry as a readout, which is quite exciting. I myself am in this field of radical S-adenosine methionine enzymes, and one of our needs has been the ability to understand these iron-sulfur cluster cofactors and their redox potential as a function of intermediate states in catalysis. And so I and a number of others in this particular area, as well in other areas, have been collaborating with Sean, who is the emerging leader in this particular field, to look at these metalloproteins using this particular technique. And so without further ado, let me welcome Sean Elliott.
Green light now? Okay, there we go. Sorry. Red light before, green light now. Okay, there we go. So, yeah, now too loud. So I did want to just highlight the other folks that are from my lab that are here with us. Pierre and Kim and Leon and Zhang will be our trainers. For those of you that are taking the interactive module that we have prepared for you, that will focus on both sort of the wet chemistry side of how we do some of the things that we can do here on a bench top, which is not exactly like our natural apparatus for working on very air-sensitive proteins that we might need to do in a glove box, but also a dry side of the experiments of how we analyze data, how we work up that data. And Pierre asked me in particular to make sure to highlight the point that we will be making use of a software package that is available. It's called QSOAS, written by Vincent Formand, who very nicely has shared with us the most recent publicly available version of that software package. And so we do ask that you try to come, practice like you play, come to our sessions prepared, and bring a laptop with that installed. It is readily deployable on most platforms, we think. So, and if not, we will have some laptops that could be used as well. But that would help if you can install that already. And again, it's on the Dropbox folder, and it's not huge like some other software packages. Okay, so today, what I want to do at the next 90 minutes or so is to try to give you a sense of why we do the kinds of experiments that we do, and again, to sort of go through some of this basic theory of electrochemistry and electron transfer, and then take us through some of the real practicalities of doing experiments and some model studies or little short snippets of details about the kinds of work that have been produced by my group and other groups to understand enzymes as catalysts. And so the idea for you all is that perhaps you may be interested in reduction potentials, as Squire highlighted, of individual interesting redox cofactors, or perhaps electron transfer kinetics, or coupled processes, or catalytic events of some kind or another, and want to use electrochemistry as a tool for trying to understand those redox-based properties that may or may not be able to be coupled directly to spectroscopic properties. And so that means, with the standpoint of different kinds of cofactors that exist in the biological context, frankly, a sort of traditional view would be to say that we are limited in biology by the window of stability associated with water. And what we are finding increasingly is, as we look particularly across the world of iron-sulfur clusters of different kinds, that these now, depending upon the specifics of the coordination environment, the proteinaceous environment around those clusters, and their composition, that these can span an enormous range of potential, and that those potential limits can tell us things about their latent reactivity, the kinds of chemistry that they can and cannot do. So this type of question of just trying to understand the diversity of redox potentials associated with your system of interest might be a part of your motivation. It's certainly part of ours. So in terms of the general outline of the talk today, we are going to start with this idea of some theory, very basic background electrochemistry, and again, from to take a nod from Serena, how many people have actually been taught electrochemistry before, formally speaking? So I'm guesstimating 20 hands or so. That's good. I mean, that's actually pretty good, quite honestly. It's pretty rare. It's increasingly rare in the undergraduate or graduate curriculum to be able to have an actual class devoted to electrochemistry. I was not taught electrochemistry as an undergraduate at all. I was a graduate student at Caltech, as Squire highlighted, and we had an inorganic chemistry and electrochemistry seminar series, and I managed to fall asleep in every single electrochemistry seminar. Every single one. It was a record, and I'm proud. And then we'll take you through some examples. I'll take you through some examples in terms of specific metalloprotein kind of problems, get into some of these thorny practical details of how we actually do this kind of work or try to do this work well, and then engage in this idea of electrocatalysis and the types of problems and, again, the complications that can arise when looking at electrocatalytic systems. And then I'll mention again a few additional points about potentiometry and remind you again to try to install SOAS or QSOAS. Okay, so to start with electrochemistry as a sort of general tool, the idea is that, of course, we need to have some kind of material that we're going to analyze, and this is the kind of work that my group likes to do, of taking a metalloprotein of some kind, in this case a cytochrome C nitrite reductase, and then making it ride the lightning. This is what we do in the Elliott group in the world of protein electrochemistry. You want to use electrons or monitor a flow of current to tell us about things. And of course, to build up to that copy infringement image, we need to start first with thinking about what's happening at an actual electrode. And so, again, it's sort of very, very old type of thermodynamic description of what is occurring at a surface, where that surface is going to undergo some type of charging effect due to a very close layer of analytes that will exist in proximity to that surface, things that can be further out that will contribute to the electrostatic environment, that will contribute to charge overall, and that there will be dynamics associated with the movement of these molecules up to and away from the electrode surface. And so that sort of fundamental picture has to be kind of impregnated in your worldview of whether or not we want to try to have a metalloprotein there in some type of cartoon fashion, whether that metalloprotein is going to be just physi-absorbed onto that electrode surface or covalently attached through some very clever chemistry, some of which I'll try to highlight today. That's a choice that you can make, but our beginning point really is thinking about diffusion and diffusive properties. And so that electrical component, that working electrode, will be part of a circuit. And so, again, just very rapidly, I'm going to step through this idea. If we imagine having a circuit with a set potential that we're going to apply, if we close that circuit, we can watch in a time-dependent way of how we can have an applied potential. And at that electrode surface, if you want to think of this little gap that is associated with a capacitance, as indicating what is occurring at the electrode. The electrode is going to charge and discharge in a way that is associated with that capacitance. That's something that we can't get rid of. We can't escape, but we have to account for, and we can account for in terms of what a blank, if you will, electrode response is going to be. In the same sort of way, if we imagine, well, we're going to move current, so if we apply a constant current source to that same very simple circuit, that there can be a fundamental behavior that will be at work as a function of time, as we have applied that current to the system. And as a function of time, if we're monitoring the potential now, the potential will be changing as a function of time, associated with the capacitance once again, and that there will be a fundamental resistance as well that will be a part of that cell. And so I mentioned these things in part because they are part of the sort of basic convolution of events of the physical chemistry that are associated with the collection of a given voltammogram. So we put these things together so we can actually have a voltammetry experiment where we can sweep the potential, and that's what's shown here. As a function of time, we're sweeping the potential from some range that we set as an experimentalist. Ultimately, what we have in a linear sweep voltammogram is something where we will rise in terms of current as a function of time, the output that we want to monitor, and that current will change as a function of time, ultimately arriving at some value that is associated, once again, with that capacitance, that stuff that is occurring, whatever is occurring at the electrode. And that stuff might, again, include our metalloprotein, our redox center of interest, or a small molecule of interest. But that will be within there, as well as with whatever is associated with the electrolytes that are in our electrochemical cell and the material associated with the actual electrode. And you'll notice that there's a V, or nu, a V here that indicates scan rate. And so that is basically, again, the time scale associated with this linear sweep. And it is absolutely proportional, as indicated here, to the resultant current. So we will see this come out now and again of how we can think about voltammetry as having the sort of plus and minus associated with it, that we can control or monitor the changes associated with voltammetric response or current response as a function of timescales. We are going to control the timescale of the experiment fundamentally on the basis of how quickly we raster this potential backward and forward in a cyclic fashion if we're going to engage in a cyclic voltammetry experiment. Or we may engage in a chronoamperometry experiment where we're just monitoring current as a function of time. And I'll come back to that again as well. And so ultimately then, why one has these sort of duck-shaped voltammograms, as they're frequently referred to, is that we're going to raster back and forth in time, and regardless of whether or not we have an actual molecule that we care about in solution or not, the basic charging and discharging of the electrode will follow this type of current profile. And so that aggregate voltammogram ultimately has some curvature associated with it that is associated with the charging up and discharging of the electrode and the turning points as we swap our direction of scan. And we cannot avoid that, but we do need to monitor that. This will be dependent upon the scan rate associated with the experiment and will be a hallmark of the kind of material that we use. So when we get into talking about electrodes, as Squire mentioned, a lot of protein electrochemists tend to use graphite as a material or some type of carbon-based material. And the other convention is otherwise to use a metallic material like gold, possibly silver, where the scale associated with those capacitances will be fundamentally different as well. And so then, if we do need to think about diffusion, if we're going to consider diffusion voltammetry, the sort of key points for us are that, that really does start with thinking about the fixed laws of diffusion in terms of a flux, in terms of how concentration of some species, some analyte that we care about, is going to change as a function of time. And then that involves a diffusional coefficient. Sort of the key point for us is that those diffusional coefficients are things that we have to know if we're going to actually be able to quantitatively determine what a voltammogram should look like or some other electrochemical experiment should look like. When we think about those currents then that will result, they are always going to depend upon the individual diffusional coefficient for a given species that we care about, and then that will, again, be convoluted with the change of concentration associated with the distance component, where the distance now would reflect the distance away from the electrode. And so the idea being that, again, if we were going to gauge that sort of thought experiment of saying, well, what happens in a potential step if we swap the potential from an open circuit potential to having that circuit on? If we imagine an oxidized species that exists in solution as we were to go out from the electrode surface, and so this would be right at the electrode surface, and as we step away from the electrode surface, there will then be a change of gradient associated with the concentration of that oxidized species, and then that changes as well as a function of time. In the same sort of way, we have a complementary building up of the reductive species as time goes on, and as we are at the surface of the electrode versus further away from the electrode. So the sort of key point being is that diffusion sucks. It's kind of the way that I look at that fundamentally, that we always have these multiple variables that we have to keep track of, and those rely upon diffusion coefficients. And most of the tools that are typically deployed for diffusional voltammetry, particularly in the world of electrocatalysis, all assume that all the diffusion coefficients that you care about are going to cancel. And so you don't have to really know or measure them independently. That may or may not be true. And so, speaking of measuring actual diffusion coefficients, that certainly can be done, and it can be done rather simply in terms of a potential step experiment, employing the so-called Cottrell equation. And so, if we now have, instead of a voltammetry experiment where we're switching backward and forward a potential in a time-dependent way, if we just step the potential once as a function of time, Cottrell, a famous electrochemist again, demonstrated this empirical relationship would hold, again, where we could extract out a diffusional coefficient with respect to our known concentration of, in this case, an oxidized species getting reduced as we step through this potential regime, and that it would have a time dependence as well. And so that Cottrell equation is plotted for you here, and the idea being that, again, depending upon the diffusional coefficient, these behaviors of concentration profiles as a function of time and distance change correspondingly to whether or not we're a big molecule or a small molecule. And the diffusional coefficient for something that is going to be a big molecule can be drastically different from that of a small molecule as well. So how do we deal with diffusion if we are going to be stuck in a diffusional mode? We can consider trying to remove the constraints of diffusion by changing up our electrode design. Instead of having a static electrode, it's conventionally utilized to have a so-called rotating disk electrode, or RDE. So that's what's illustrated for you here. We can imagine, and you'll see some of these in the practical components as well, where we have an electrode that then is hooked up to a rotator, where this circular arrow with a frequency omega indicates that sense of how rapidly this electrode is rotating. And if we're studying diffusional things that are going to be electroactive, then we can sweep up those diffusional things up to the electrode surface, where we have a hydrodynamic flux that is generated through the rotation action itself. And so that can provide a constant concentration of molecules at the electrode surface. So we don't necessarily have to worry about the diffusional component being avoided, as long as we can assure ourselves that electron transfer characteristics are going to be sufficiently fast. Now, when we step into the world of adsorbed species and protein films, as they're referred to, the idea being is that if we have a catalyst now, or a protein that is adsorbed to that electrode, that's not moving. But what might be moving is a substrate concentration, a concentration of constant substrate that we want to bring up to the electrode surface and control and monitor its reactivity. And we don't want that to be depleted due to diffusional characteristics. And so a rotator becomes a very useful tool in that context. Additional complications from the standpoint of electrochemistry, and I'm just going to step through again some of these historical depictions of reaction mechanisms that might be at work, are that, formally speaking thus far, all we thought about are redox reactions, right? Just saying I want to move an electron, I want to take an oxidized thing and reduce it, I want to take a reduced thing and oxidize it. Well, that's very simplistic. It might be appropriate for your system of interest, but quite frequently, redox reactions can also be coupled to chemistry, and so those steps, those chemical reactions might occur previous to or following the electrochemical reaction. And again, if you hit the electrochemistry literature, you'll see that there's a parlance of C and E for chemical and electrochemical steps that are used to describe those two different reaction modes. And that includes the scenario where you could have a so-called catalytic reaction, where the preparation of a electrochemically prepared state then becomes reactive and regenerates the species that then can once again prepare and participate in that electrochemical reaction. And so the idea being that these complications are going to be other issues that can change how we're going to think about electrochemistry as a whole. So if we want to have very well-described equations to let us recalculate what these voltammograms should look like so we can get out really quantitative information, there are a number of regimes that are useful. One of those regimes, which I'll introduce very briefly because it's not quite practically useful, is the use of an ultramicroelectrode. So in the case of this type of regime, we now have a very small electrode so that diffusional properties can be matched with the length scale associated with the actual experiment. And so under these constraints, the idea being that we can arrive at equations that, again, allow us to specifically relate how the current is going to change as a function of time and how that current change will be associated with sweeping the potential, not just stepping the potential. And so from those perspectives, we can end up through a set of equations that will give rise to something that frankly looks like a titration as we sweep through the potential and eventually arrive at a regime where diffusion is supplying molecules as rapidly as they're going to be as rapidly as they're going to be electrochemically interrogated at the electrode surface without having to use a rotator. The challenge, of course, with this is that you then have to make ultramicroelectrodes, and there's a sort of art associated with that, and that's kind of a non-conventional approach for the type of work that we'll be doing today. So again, perhaps frustrating that I introduced something only to discard it, but it is analytically pure, and so it's attractive from the standpoint of from the electroanalysis perspective. So instead, we will make use of bulk electrodes, where bulk I mean things that you can see with your eye. So these are millimeter-sized devices, or it could be smaller still, but not necessarily on the micron or submicron scale or nano-scaled electrodes. And engage in voltammetry typically as our sort of beginning place, thinking again about a cyclic potential sweep that will go backward and forward, and then generating voltammograms as a result. And so if we have a voltammogram now, we can think in terms of an American convention or European convention, which I'll introduce in a second, where the key idea is that the scale associated with positive and negative signs of potential are swapped. And that means in the American convention that cathodic reductive processes are occurring on the top and anodic processes are occurring on the bottom. And regardless of convention that we utilize, the key ideas being of the equations that describe this diffusional voltammogram now, as it's shown for you here, that there's a peak current associated with both halves of the wave in this reversible reaction, and that those are proportional to the scan rate once again, but the square root of the scan rate, not just the absolute scan rate as well. And so there are traits then of a diffusional voltammogram that one can look for to try to get a sense of, is my system a reversible system? Is this a pure redox reaction? Or are there redox chemistry that is associated with other kinds of chemistry? And so that includes doing things like examining what are the actual peak positions and what is the difference between those peak positions that should be well described. How does the peak height, the absolute magnitude of these current signatures, change as a function, again, of scan rate? And does it have a square root dependence versus a linear dependence, which we'll see is important? Once again, this is ultimately going to be linked to a diffusional coefficient, which we might monitor through the Cottrell equation type experiment, the potential step experiment I suggested before. And of course, will depend upon the concentration. The more stuff we have, the more current we get. And that's perhaps not necessarily that unobvious. And then we can read out, in this case, the potential directly, the thermodynamic potential for the redox couple, the standard potential that we are interested in, from the standpoint of the average of those two peaks. And so this has been done for the diffusional voltammetry of proteins. And so this is a case from the lab of Marco Sola and Battistuzzi, studying cytochrome C2 from Rhodobacter palustris, Rhodobacter pseudomonas palustris. Again, a relatively small cytochrome, so about 100 residues, molecular weight of about 14 kilodaltons. It has a single C-type heme cofactor, we imagine, with his-met ligation. And so this should give rise to one would predict, a sort of simple one-electron redox couple associated with the iron 2-3 redox couple. And so these are the data from their nice paper, which show, again, that there's a good peak separation, indicating that there's no funny business, if you will, associated with that. This is now a gold electrode that's been treated with mercaptopyridine. We'll talk a little bit more about those electrodes in due course. But if you go through the sort of details of the paper, the sort of promise of electrochemistry, or one of the promises of electrochemistry, is a sense of sensitivity, that we are very good at counting electrons, so we can usually analyze very small samples. But if you dig into the details of this paper, you see this is on a relatively speaking large sample volume with a relatively high concentration of about 200 micromolar. So that means about 1.5 mgs of protein are associated with this particular experiment, which is not that sensitive, 100 nanomoles. And so, again, we can rapidly read off the potential, and this is, if you will, a recyclable experiment. This is not burned in a synchrotron or something like that. You get the protein back at the end of the day. But in terms of this diffusional mode, where it can lack that sense of sensitivity, this, again, has to do with the relatively poor diffusional coefficients associated with the protein and its relatively big size. And we'll see that the size of these currents, now on the microamp scale, are going to be something that will be an issue. Let's just put it out there like that in terms of whether we want to be able to address lots and lots of different things. That could be proteins of increasingly large size that will occupy more and more physical space on a given electrode. So American conventions be damned. We will make use, largely speaking, of the European conventions because they're better. They're better, and so the idea is that now we'll have anodic processes have a positive sense just because it makes sense, because positive oxidations, negative reduction reactions, that makes sense. But everything else is the same, basically. So we now have negative potentials to the left, positive potentials to the right, and you can all adjust. So very good. With respect to that, again, this idea of reversibility, whether we have a pure redox reaction or things that are then coupled, become very much into play. So with respect to a diffusional voltammogram, just from the standpoint of the conventions that are utilized, again, making use of the purely reversible case requires that there's a peak separation predicted by theory. Then once you start to separate away, you have something like the dot dash line, which indicates, you can still see an oxidation and reductive wave, half wave, but now that peak separation is great, and you would call this a quasi-reversible reaction, and that's compared to the dotted line, where you have a gross distortion of voltammogram, and you can't see the return wave and these so-called irreversible features. That doesn't necessarily mean that you're bad, but it is different, and it does sort of change with respect to, it's an irreversible redox feature, and it probably tells you that can tell you several things, one of them being that maybe there's another chemical reaction that's occurring once the system first gets reduced. And so that's an opportunity to learn. So this idea, again, of if we have these coupled phenomena at work, whether we're considering a preceding chemical reaction, what matters is the relative time scale. And so this is, again, one of these opportunities that voltammetry brings to bear, that you can very easily just dial up or dial down the scan rate associated with the experiment. And so let's put some numbers on that. For respect to sort of slow scan rates, the things that we'll talk about, will be on the order of a few digits, tens of digits of millivolts per second, whereas fast scan rates are on the order of volts per second. And then contemporary equipment, and not the kind of equipment, frankly, that we brought here, lets you get up to thousands of volts per second. So, many orders of magnitude difference of time scale can be accessed in terms of the potential sweeps associated with a given experiment. But the key point being is that whether or not we are moving on a time scale that is going to be appropriately slow enough such that B is always going to be available so that we can engage in the electrochemical reaction, that might look reversible in effect. But if we change the time scale associated with the experiment, we might lose that sense of reversibility. And the same is true for a following reaction, where now we need to make sure that our A is always going to be there, but that the B will be present as well and not consumed to form C too rapidly, if we're going to see a case that will look more or less reversible. Again, the point that I want to allude to with respect to quasi-reversibility or irreversible reactions are that the coupled processes that are associated with these types of chemistries translate into a difference of the location of that peak response. And so when people show a voltammogram, just to sort of keep this in mind, that's irreversible, this couple that, this spot in terms of potential, let's say 0.1 volts, that can't be the thermodynamic potential associated with the redox reaction because it is distorted. It is pulled away from what that thermodynamic process, that thermodynamic redox reaction should be by virtue of this coupled reaction. So the readout, if you will, is skewed in that sense, but can be understood simply by changing the time scale, hopefully by changing the time scale associated with the actual electrochemical response. So many of you probably work with metalloproteins or redox cofactors or even small molecules that have not one redox process associated with them, but multiple redox processes associated with them. And so the standpoint of having multiple redox cofactors or events, if you think about redox active ligands as a very interesting area of inorganic chemistry, translates into, in the voltammetry, of having potential multiple features. And again, whether we're just considering here diffusional voltammetry, that same process is possible. And so one can consider formally, and we'll come back to this again, the notion of how, if we have two different redox couples, the question in some sense is how separated they are with respect to each other. And if we can think about them as being independent events or simultaneous events that effectively are two different electrons stoichiometrically moving, but with no interaction or bias between them to give rise to a sense of cooperativity, versus what occurs when those two potentials are actually inverted with respect to each other, such that the second electron becomes, if you will, easier to undergo its movement after the first electron redox transformation has already occurred. Whereas when those potentials are very well separated, we could imagine, if you will, generating in the voltammogram just a single one-electron redox couple, preparing, if you will, if we held the potential poise at this point of a semi-reduced state, and then the second potential, the second redox couple, the second electron, can be interrogated, if you will, separately. And that we will find in the world of adsorbed proteins, that we'll come back to this point again, different kinds of cofactors where those two different regimes apply entirely. In the same sort of sense, we can have different kinds of scenarios, whether if you're in diffusional mode or in adsorbed mode, or with multiple redox events, where they may not necessarily behave the same. They may not be two individual redox couples. And so we can have, again, a reversible wave followed by an irreversible wave, where we should have that sense of separation, but don't, and it skews the entire shape of the voltammogram. We can have the reversible feature then followed by an irreversible feature where, again, they are coincident potential. And so because of that secondary event, we never get back our oxidative feature in this case, even though there's one redox couple that is innocent, it should be reversible. And then if we swap the ordering of the sense of reversibility, again, the idea is that we could have our two interrogatable events where one of them is simply irreversible with respect to the other. And if they're both irreversible, we might have something kind of horrific that looks like this, where we don't get back any oxidation whatsoever, even though the potentials are separated from one another. So with respect to metalloproteins and a lot of the work that we're now follow on, we're going to get rid of diffusion. Somehow we're going to make diffusion at least be a, relatively speaking, small component and rely upon our ability somehow, again, to arrive at an immobilized system of where we're at least limiting the extent to which diffusion is a problem. And if we have this immobilized mode, things can become better from the standpoint of mechanical stability. And some people are interested in electrochemistry as the principle for generating a device or a sensor. And for our purposes, at least the standpoint of the electroanalysis, using the current shapes to understand things becomes a little bit easier. If we're in this mobilized mode, the sort of tutorial landscape now is that in theory we should have zero peak separation whatsoever, such that the midpoint potential, that thermodynamic potential, is exactly the same. Whether we are actually taking the average or not, they should be identical. Now, realistically, we'll see in the world of metalloproteins that is usually not zero, that usually there's at least some smaller than 60, usually like 10 or 20 millivolts peak separation, and I'll discuss a little bit more about where that may come from in the world of big macromolecules. With respect to the peak current issue, now we have a difference with respect to that scan rate. The scan rate now has a linear dependence, which means that we can rapidly use the linear dependence of the scan rate versus a square root dependence of the scan rate to peak current to tell us, do we have a diffusional-based system or do we have an adsorbed system? And now as well, we can see that there should be a clear squared dependence on the number of electrons that are associated with the redox couple. And so that becomes, again, one of the sort of virtues associated with an immobilized system for things that are going to engage in 2 electron transfers versus 1 electron transfers. Then that becomes very clear on the basis of the peak height and as well the peak width, which I did not really allude to before, but this idea, there's our peak height as a proportional to the scan rate. And with respect to peak width, that there are now is a good description in terms of how the peak width should change as a function of the number of electrons that are associated with the redox couple, and I'll talk more about that in a little bit. and as well that this should be dependent upon temperature additionally. And then finally, again, now we could read out that area, usually quite easily, that tells us about what's referred to as a surface concentration or electroactive coverage or something like that, where that tells us not about the total number of molecules that are absorbed on the electrode. To do that, we would need to have some other kind of surface spectroscopy or surface-mediated type of readout to tell us about the absolute amount of things that are absorbed in a monolayer or multilayer, but it does tell us about the number that are talking to the electrode, if you will, the amount of current that has been passed, so the number of molecules. So now with respect to that sort of general background, we can now step into some more specific metalloprotein examples. So thinking back to our cytochrome C2 example from before, now if we immobilize a cytochrome, and so work from my group in collaboration with Cara Bren's laboratory, studying various monoheme cytochrome Cs from different bacterial sources, we can engage in the same kind of experiment as before, but now with the voltammogram, again occurring in this case on a gold-based electrode, where we can directly analyze how the peak height goes as a function of scan rate and see that that's a nice linear dependence, while we do not see necessarily the zero peak separation that one would anticipate. Importantly, again, the overall magnitude of these currents now are significantly less. And so sort of the key point with comparison to before. Before in our diffusional voltammogram, we had these microamp currents, and now we have really nanoamp currents when we get down to it and subtract away that background capacitance associated with just the charging and discharging of the electrode. And so if we utilize those peak heights, we again can make use of the equations that describe how the surface coverage can tell us about the number of things that are actually absorbed. That depends upon scan rate once again. And so for the scan rate that's utilized in this experiment with a peak height of about 3 nanoamps, we basically have a picomole. Picomole. Now we're talking sensitivity. That sounds good. So this is one of the, again, the sort of points with which now we are sacrificing, if you will, intensity for the ability to examine relatively small quantities. And hence, one of the rationales for why I've joked in the past that protein film voltammetry is essentially a very cheap date compared to some of the other methods that we'll talk about throughout this course with respect to the amount of experiments that can be done with a small amount of protein, because we are still quite good at counting electrons. Okay, so another similar example of just thinking about, well, if we can look at one redox couple, can we or others look at multiple redox couples? And so this is data regarding flavocytochrome C3, FCC3, which is a fumarate reductase from Shewanella. It's found in lots of different Shewanella species, and you can see it has panoply. It has 4 different heme cofactors, and something that might be less obvious what that is, but there's a flavin embedded as well as the actual active site associated with this cytochrome. And so in the same type of analyses before, and this was work conducted by my former postdoc lab in the Armstrong group many years ago now, where you can see, again, on the background of now a carbon-based electrode. So this is the big background capacitance associated with carbon. These relatively speaking small, but still quite discernible peaks, which also has a very high degree of sharpness associated with that, where we can deconvolute the components that are associated with those so-called non-catalytic features, these features that aren't associated with catalysis, just the pure redox cofactors themselves. And by, in this case, varying pH, it becomes quite clear that one of these features is moving around while the others are less so. And this type of approach, then, of sort of generating what could be a complex envelope of data and then deconvoluting it into components that we can well describe on the basis of the electroanalytical equations that will indicate that overall shape for the individual component, can be arrived to generate these nice fits. And so one of the reasons why, in this case, we could deconvolve this into so many components, and it's frequently been the case in the world of many flavo-containing enzymes, are that flavins are a 2-electron redox cofactor. They do behave electrochemically as a 2-electron cofactor, and so they have that sense of cooperativity that gives rise to sharpness 4 times as high, 1/2 the peak width on the basis of the equations that we've talked about thus far. So it's very clear that, that it's undoubtedly a flavin, and that these shoulders must be due to the overlapping components that are all there, that are all a part of this composite electrochemical response. Okay, so this idea of cooperativity, again, we're going to go a little bit down something of a set of equation wormhole, has been well described before, formerly first by Laveron, and then has been metamorphosed over time. But the idea being, again, that we can describe these type of equations that show the dependence of current, the interdependence of current and potential for now a 2-electron redox couple. And the sort of key point being, again, as before, if we have well-separated redox potentials, then we can see these as two individual one-electron events. Then as those two potentials become closer together, first coincident and then swapped in terms of their location for a sense of cooperativity, that is where we see the emergence of this sense of cooperativity as a result. This sharpening, this intensifying, and the narrowing of the overall peak signature. So when people, such as ourselves, are investigating the behavior of possibly cooperative redox couples, trying to monitor that sense of sharpness is quite widely utilized. Another equation that is frequently utilized but does not have a real physical meaning is illustrated for you here, where instead of having a specific term for having two electrons involved, you break that apart into a number of stoichiometric electrons and the number of so-called apparent electrons. And so this is the manner with which one can arrive at that description of delta that has a n-app feature in it. So n-app does not necessarily mean anything, but is a way for you to phenomenologically say this is a sense of cooperativity or something that is deviating from the theoretical construct, whereas you can still treat any type of electrochemical data on the basis of the actual Laveran equation that I showed before to give rise to that sense of the separation of individual components. Okay. So with respect to voltammetry compared, in some sense compared with other electrochemical techniques, a sort of key idea to keep in mind as we consider multi-electron redox processes are that these voltammetric potentials that we're going to read out aren't necessarily telling us about microstates. And the sort of idea of microstates that you might think of saying, well, what happens when one electron has gone into one cofactor, and what is the impact of that one electron going into one cofactor on the redox potentials of the other cofactor? It's the type of question I get asked a lot. I mean, can we extract out that information? And the sort of simple answer is no, we cannot, simply from voltammetry alone. And so that's illustrated for you here. Figures taken from this wonderful review written by my friend and colleague, Christophe Léger, at the CNRS, that describes exactly this scenario of thinking about a scheme where we could imagine there being pure thermodynamic potentials associated with the redox poise, let's say the redox reaction of A when B is held in the oxidized state, and then the complementary set of microscopic states that could arise at as well. And so the idea of the scheme that is shown here is to consider two different scenarios where we might say, formally we can set two of those redox couples as being the same and just as an arbitrary value of 0, and otherwise not being the same. And if we think about what we're going to engage in terms of an electrochemical analysis, we're going to monitor data that looks like this. And so if you extract out data that looks like this, it is very hard to know if my data looks like the red trace. Is it really the scenario like the red trace where there is no redox cooperativity or anti-cooperativity associated with the system? Or is it in fact really the blue case where there is a sense of interaction potential between those two different redox cofactors? So sort of take-home message for us is that with protein electrochemistry or any electrochemical tool, if we want to get at this idea of microstates, we really need to have another coupled technique. We need to look at how an individual spectroscopic feature will change as a function of potential, and that is work that's been done in the case of multi-heme proteins very nicely by Ricardo Luro and his colleagues in Portugal, where one, in some cases, has a specific reporter on heme state as a function of redox potential. Okay. That is to say, so whereas we're going to measure these thermodynamic potentials, bulk potentials, describing as the whole, we still can examine the sense of cooperativity. We've seen this before for flavin enzymes. We can see it as well in the case of some, but not all heme proteins. So previously my lab has investigated cytochrome C554, just as one example, where for our purposes all that really matters is that there are a series of 4 heme cofactors. Intriguingly, where 2 of the hemes are thought to be very close in potential, and through spectroscopic work conducted by Mike Hendrich's group, those have been assigned to the hemes on the extrema of the molecule, whereas the structure was solved by Tina Iverson and Doug Reese's lab in collaboration with Alan Hooper. Cytochrome C554 is responsible for picking up 4 electrons from hydroxylamine oxidoreductase, and Sue Polchu, a former graduate student in my lab, found indeed that we can see individual redox couples associated with these 2 low potential hemes, and then an aggregate signal that can only be understood in terms of invoking some sense of cooperativity, whether we model that in terms of narrowing of individual redox cofactors or consider this a single cooperative redox cofactor. And so the key point being is that by monitoring the shapes associated with voltammetric features, we can still get at a sense of if there is a net cooperative event, whether or not we can truly model that best on the basis of swapping of individual redox potentials or a sense of microscopic cooperativity that we would otherwise need to have another spectroscopic tool to read out. We've as well monitored cooperativity in disulfide bond electrochemistry, and this again gives you a sense of just how low we can go in terms of the overall magnitude of these currents, where these are now tiny currents, nanoamp currents that we're picking up on the background of our capacitance of the electrodes, looking at disulfide bonds, where it's very clear that they are narrow and sharp, and that they have a narrowness that actually disagrees with what you would predict on the basis of theory, but one that increases, it becomes more cooperative, if you will, more like a true two-electron couple as we increase the temperature. And this, in this case, and we'll discuss this in a little more detail, this is a sort of scenario where there's this absolute interplay between how well we can have things absorbed, in this case absorbed onto a carbon-based electrode. As we heat things up, eventually they simply fall off. They simply will desorb and will not behave nicely at all in that same regime, but we can capture a look at them while we can and see that they are in fact behaving like two-electron redox features. And then additionally, this idea of being able to examine something that might be seemingly innocuous can give rise to an unusual sense of complexity. So in the case of Azotobacter finlandii ferredoxin 1, we have two different iron sulfur clusters, a 3-iron 4-iron sulfur cluster and a 4-iron 4 sulfur cluster. And in some classical work, again, from the Armstrong lab, it was found, in fact, that there are 3 different redox couples that can be observed. One that is undoubtedly a two-electron in nature, again, due to the intensity and sharpness associated with it, which has been ascribed, but never really verified, but it's sort of ascribed to the 3-iron 4 sulfur couple 3-iron 4 sulfur cluster undergoing a two-electron process, whereas the other 2 features are associated with the 4-iron and 3-iron cluster, respectively. In the same sort of way, I couldn't come to Penn State and not mention our work with Squire's lab, where, again, we could examine, and this also highlights how, where it's capable of taking a protein that has multiple redox cofactors, in this case BTRN, examining the voltammetric response of the wild-type protein, where it's clear that there are 2 redox couples. But again, the sort of beautiful thing about electrochemistry is that you don't need spectroscopy. The terrible thing about electrochemistry is that you don't have spectroscopy to tell you which is which. So in this case, exactly, this is a problem we run into all the time. So we can get data, but how do you interpret it? And so in this case, we needed to have a mutant that removes the S-adenosyl binding cluster, basically the active site cluster, to tell us exactly which potential is associated with the so-called auxiliary cluster in this case. So again, just sort of highlight to you from the standpoint of saying that we still need to have additional components, additional techniques to help us understand our own data, frankly. And sort of another caveat or warning, if you will, is to think again about how, as we get to larger and larger enzymes, the nature of these currents are just bound to get smaller. That there's a fixed size of a given electrode that we can utilize, even if it's on millimeter, even if you go centimeter. There's still going to be a relationship between the overall capacitance and what the sensitivity will be for detection. And as we get to something that's now quite large, in this case, again, another FRD, or succinate dehydrogenase, a 2-subunit enzyme, which again has a flavin in a series of iron-sulfur clusters in this case, it is still evident that there's an additional redox couple, but again, it's starting to get into the regime of where these nanoamp currents are getting harder and harder to detect. And so, what is the limit with which we can make good detection? Basically, conventional instrumentation usually is high picoamp to nanoamp, although, the sort of specs of an instrument that is tricked out, can get you down to femtoamps pretty routinely, but still, it's your ability to control electrochemical noise, which is not shown here, but when you come upstairs, you will see. That's the tricky bit. That sort of this could be drowned out on the basis of electrochemical noise. That is the reality that we try to deal with. Okay. So additionally, in terms of non-catalytic voltammetry, frequently we're interested in thinking about ligand binding, whether that ligand is a proton or whether that ligand is a small molecule or a substrate that may not yet undergo some type of chemical reaction. We can think about that type of relationship in a so-called Pourbaix diagram, where we cycle through, in the case of a Pourbaix diagram, a series of states, effectively a square scheme, where we have limiting potentials associated, in this case, if we're thinking about protonation, where there's no ligand bound or no proton bound, and when ligand is bound or when the proton is bound. And therefore, there are ionization constants associated with either of those states. And again, through the just Nernst equation associated with that square scheme, we can arrive at a maximal dependence associated with the number of protons and the number of electrons. And so this becomes, again, a very useful tool when trying to understand proton-coupled electron transfer, or diagnose that might even be a component of a given redox cofactor, looking at for this Poor-Bay relationship to see are they coupled or are they not coupled becomes a key point. So again, back to BTRN, the idea being is that we found, in this case, my student Stephanie Mayako found that the atomette radical cluster is undoubtedly proton-coupled, which was a surprising finding on the basis of work that had been suggested before for other atomette radical family enzymes, whereas the other cluster, the auxiliary cluster, has this sort of weak dependence. And again, I like to show this example because this is something that's very nicely behaved. This is something that's sort of crappy, I mean, quite honestly. It's neither flat, nor does it behave a very nice one proton, one electron couple. So what do we do with that? What do we do with that? We can try to fit it to a bunch of things, but frankly, we could not convince ourselves that those bunch of things were meaningful in any way, shape, or form. Versus other scenarios that you might find in literature where you really do see a truly flat dependence. So I think the idea that us and other groups are developing is that basically when we see these sort of weak, and by weak I mean like maybe 10 millivolts for pH decade type dependence, indicates really outer sphere interactions that are not necessarily direct coupling of protons and electrons going together, but instead indicating that there are further ionizable residues in the protein environment, but not necessarily in the close proximity to the redox cofactor that might be at work. And one can have multiple components that are associated with complex redox equilibria. That's been demonstrated very nicely in the case of risky iron sulfur centers by Judy Hurst. Again, where now we can have a more elaborate square scheme where there's not just one protonation. There's always one electron in this case because it's just a 2-iron, 2-sulfur center. So we have one electron, but we have 2 protons, and so that requires a sort of ladder-like scheme. And in the case of the ordering of those pKs, sort of the key idea of where do they fall, then one can have a regime where it looks like there's a 1 proton, 1 electron coupling event, and then a 2 proton, 1 electron coupling event where it becomes quite steep as a result. And that's in contrast with other proteins like mitoneat, where again we have a 2-iron, 2-sulfur cluster, now just a single histidine ligand, and intriguingly the gray data is for the wild type where we have this very shallow dependence that you cannot fit. It is protracted in terms of the dependence. You can't fit that to a single 1 electron, 1 proton couple. It does require that there are 2 different protonation events for the single electron. And then even as we make mutations at that histidine residue, that's the data that's shown at the bottom, transforming it into cysteine, thinking that perhaps the histidine is the culprit, if you will, associated with these unusual protonation events. In fact, you can now see that all you've done is perturb those pKs, and they become quite clearly a sort of stepwise one protonation event associated with another protonation, and then followed by a secondary protonation event. So this idea of dissecting or deciphering pK values is something that we're very, very interested in. So an additional tool, again, from the standpoint of non-catalytic experiments, comes from now, instead of thinking about ligand binding or things that might be relatively speaking slow, looking at interfacial electron transfer, trying to understand the rates of electron transfer associated with a non-catalytic set of data, and how can we do that at an electrode. And so with the standpoint of a bit of the electron transfer theory, the idea is that fundamentally, and I realize this is a bit out of order, it would be great to have this portion follow David Baratan's talk, so I'll just summarize in some way. But the notion being that we can think about what theory predicts and what Marcus theory predicts in terms of an electron transfer rate, and how that there's a dependence upon an electronic coupling term, there's going to be a dependence upon what the actual driving force is, and the reorganization energy associated with the redox reaction that would be at work. And that we're going to see that the coupling will go down, the rate of electron transfer will decrease as we increase that distance. And I know later on in the week we'll be hearing a lot more about the exact pathways and terms with which we can describe that sense of coupling, as well as how we can think more specifically about reorganization energy. If we're at an electrode, it's sort of similar relationship results. Although the typical behavior that is used for describing that ratio of electron transfer rates, we can think in terms of first a Nernst equation, where there will simply be a potential-based dependence associated with that. And then an empirical or so-called Butler-Volmer, which is a sort of tried-and-true model for electron transfer kinetics, would give rise to this type of result, where again we have sort of a similar relationship between an electronic coupling factor with now what we refer to as an interfacial electron transfer rate, that rate by which the electronic coupling can occur. And it doesn't have to do with the internal wiring of a complex metalloprotein, let's say, but literally it just has to do with how well that metalloprotein or catalyst or whatever our molecule is going to interact with a given electrode. that we might be able to control or we may not be able to control. And under that Butler-Volmer regime, we would say that there's actually not going to be a dependence upon the reorganization energy as long as we're not necessarily, as long as we're not at an extreme overpotential. However, if we then incorporate Butler-Volmer kinetics with Marcus theory, the type of relationship that results is shown here for you. And again, the key point being, I don't expect you to decipher that equation, but the key point being is that basically we should reach, in this Marcus-based approach, a limiting plateau of rates to tell us about that absolute rate of electron transfer if we're at high overpotential. And so the idea of what emerges in the world of protein electrochemistry is really built off of work from Chris Chidsey looking at ferrocene chemically absorbed onto a gold electrode. And so ferrocene, for those of you that don't know, is kind of like the hydrogen atom for electrochemists. Instead of for like a hydrogen atom for physicists, we use ferrocene for electrochemists. It behaves so beautifully and gives rise to very nice voltammetry. And in this case, ferrocene would be covalently attached to an alkane thiol, further covalently attached to a gold-based electrode. And the idea in the case of these experiments is that one can find, as one increases the rate of a cyclic voltammetry experiment, and that's what's shown here, there is a peak separation that is engendered. And that peak separation reflects the rate at which we can have electron transfer occurring into the ferrocene and back out. Or one can examine a transient mode as, again, a sort of potential step mode where the magnitude of the step was varied in the case of the science paper and the unimolecular rate determined directly from the kinetic traces of current. So again, this is a current-based readout. And so that type of analysis gave rise to the following plot, which then describes how Butler-Volmer theory, again, would give rise to the dotted line where we don't see any tapering at all of that response versus the actual data for a series of samples, which shows that there's a limit with which that plateauing behavior should occur, indicating that ultimate rate of electron transfer. This has also been replotted nicely in a review by Lars Eucken that I wanted to bring to your attention, which just shows, gives a little more context as well to build up the equations that are associated with how that varies as a function of predicted reorganization energy. And so in the metalloprotein world, again, it's going to be harder, I should have said, for us to engage in these kind of kinetic trace experiments because we have such small currents to begin with because of our big metalloprotein molecules. But we can usually look at the readout of that the peak position dependence as a function of scan rate. So the approach that is more typically utilized is based on that type of what's referred to sometimes in the literature, although it kind of rose and then died, like the Hindenburg, of referring to these as trumpet plot analyses. And so you can sort of see this vaguely trumpet-like shape indicating as we go to faster and faster scan rates, the peak separation gets larger and larger. And the key point being, from the standpoint of the equations that describe this relationship, so what we really care about is this flattened region, this region where we have a linear response, and it's going to be that intersection point which tells us about the relative rate of electron transfer. And so if you're trying to measure interfacial electron transfer rates, but you can't get substantial separation, you can fit that, but it will be kind of nonsensical as an ultimate result. You need to be able to get out to whatever rate for your system is going to give rise to that type of Marcus-like behavior. And so this has been done for various metalloproteins, and with rates that go from very slow, meaning like 0.1 per second, 0.05 per second, to rates in this case that I'll show you are very fast, of 10,000s per second for electron transfer across an electrode. So one of the best examples, best comparative examples of this comes from, again, a study of a, relatively speaking, simple cytochrome from Aquifix aeolicus, where Aquifix aeolicus will actually process cytochrome C555 differentially and either include a site of lipidation, which can then be intercepted and attached to a gold electrode, or will proteolytically remove that additional bit of N-terminus such that you have the so-called soluble form of the same cytochrome. So this, in some ways, is a great experiment because we have we don't have any problems. One will imagine we're not going to have any problems with differences fundamentally of the thermodynamics associated with the redox reaction at the heme cofactor. The heme environment is the same. All that's different is the way in which it's attached, and that should give rise to our ability to assess the difference associated with electron transfer rate. So that's what's shown for you here in terms of 8 volts per second, looking at the difference of those voltammograms, where in the case of the membrane-bound form, these are very much superimposable. We have that nice zero peak separation that we would imagine. At 8 volts per second, already cytochrome C55 soluble form shows a significant asymmetry. And then that can be observed as well in terms of looking at a function, in the case of this paper, again, from Frauke Bayman, which was a visitor in the Armstrong lab, of how that dependence would also vary as a function of ionic strength.
and that the soluble version, again, gives rise to these time scales, which now are slow, much slower compared to the membrane-bound form, which, again, at high ionic strength gives rise to these blazingly fast rates that are about 10,000 per second. The key point being, again, that the equations that are associated with the governing this behavior are so interconnected that really the best that one can do is say something is fast, something is slow. You're not going to be able to argue that you can determine the difference between a factor of 2, and anybody should not have their paper accepted wherever it was accepted. Basically, you can tell something is going to be significantly fast on this log-based scale versus something that's going to be significantly slower. The best you really can do in these scenarios is order of magnitude type of behavior of electron transfer rates. Yes?
Is the soluble form adsorbed to the electron, or is it just
Yes.
in solution?
No. So I should have said, so in this case, this is sort of an analogous experiment. It is adsorbed onto a gold-based electrode, but it is not covalently attached to it.
Okay. So
Yeah.
being covalently attached.
So it is, so it is oriented and is, from the standpoint of the surface spectroscopy, it's unclear exactly what the nature of that N-terminal bit is doing. But the cartoon depiction is about, the best view that we have from the standpoint of what the prediction is of how this is behaving. But it's clear that inclusion of that, whether it is directly physically attached and oriented, helps give rise to very fast electron transfer rates. In the same sort of way, the length associated, and this might be more conventionally known to a number of you, the length with which one can think about the distance associated for electron transfer is undoubtedly going to influence the rate that could be observed. And so this has been demonstrated for a variety of simple proteins like cytochrome Cs, horseheart cytochrome C, or azurin, where one can look at the number of methylene groups in an alkane thiol that can link to that active site. Ultimately to the active site, whether it's the heme cofactor or the blue copper center in the case of azurin. And over most long length scales, where again long in this case means about N, so like octane thiol or longer, there's a linear dependence. But once you get below that point, sort of pentane thiol, butane thiol, or shorter, there's generally speaking a limitation that exists that has been in some sense hotly disputed as to exactly why this type of behavior results, and it might indicate there is a conformational gating that is at work that only can be alleviated by having slightly longer distances. An additional component that is at work with respect to this type of SAM arrangement that I'll speak about a little bit more with some graphical images in a moment, are that these monolayers have a sense of packing associated with them, and that the longer that they are, the tighter that packing is, the more uniform that packing is. And so the more monodispersed that surface would be for the purposes of electron transfer. Again, from the perspective of thinking about interfacial electron transfer in this way, sometimes we could imagine that these problems are really a virtue, because if we can control that nature of the surface, the nature of the electrode, the nature of the fundamental electron transfer rate that could be accessible, that might actually be a way for us to learn something interesting. In the case of cytochrome C554, again, the data I showed you before was on mercaptobenzoic acid modified gold, so an aryl spacer, not an alkane spacer, where presumably the conductive properties would be better, and shorter than mercaptoundecanoic acid. So that's just a C11 spacer, 11 methylene groups, terminating at the same carboxylic acid functionality, where under very slow scan rates, we're able to observe very nice data and could model it very much like before. But as soon as we would increase the scan rate, everything would go to, not a nice place. The data starts to look very asymmetrical. It looks very, graciously, we could say quasi-reversible, but then quite irreversible. The faster that we go, and that this behavior was completely reversible. That is to say, we could start slow, speed things up exactly without moving anything, dial the scan rate back down, and we have that nice reversible behavior again. So what that told us ultimately is that effectively the rate associated with electron transfer, and again, this is where we can tell something that's slow with respect to something that's modestly fast, and that in that mercaptoundecanoic acid case, that is a relatively slow rate. It's also about the rate associated with the actual HAO turnover with cytochrome C554. So our suggestion in the case of this paper is that perhaps this is an example where if you match the rate of electron transfer, we can see a lack of reversibility because the enzyme, or the protein in this case, conformationally is reorganizing. It is no longer talking to the electrode because it has received the 2 electrons it needs to receive, and then we'll start to desorb. Again, the use of time scales and varying time scale is incredibly important to try to examine things like proton transfer. the case of Azotobacter vlandii ferredoxin 1, that this is one of the canonical sort of textbook cases of the use of protein electrochemistry to try to understand how the shape of voltammograms can tell you about chemical transformations, in this case, proton transfer. And so with respect to that highest potential feature associated with the first redox couple, the 3-iron-4-sulfur cluster, the pH behavior, the Porbet diagram in this case, has never been visualized for the acidic region, but for the alkaline region is shown for here. And so this is, again, a figure that shows not just the wild-type data, but a whole series of mutants where they've slightly skewed that pKa. And for our purposes, the key point being is that we could imagine voltammetry now under conditions where either in that alkaline regime, where there should be no protons being transferred because we're pH independent, and somewhere around pH 5 or something like that, where we're clearly proton coupled, and protons should move along with electrons associated with that couple. And so as well, the idea being that this became an interesting problem because the iron-sulfur cluster itself is not exposed to the outside world. The only gate for proton transfer seemed to be, at that time, an aspartate 15. That was, again, within 5 angstroms. And molecular dynamics calculations had suggested that that would be able to rapidly undergo a transformation where it would be much closer to the iron-sulfur cluster to allow for proton transfer and shuttling, if you will, of protons back out to the outside world. And so the use of electrochemistry in this case then comes at this, the development both of mutations that would magnify the effect that could be observed by mutating D15 to E, so aspartate to glutamate, and then looking again at that basic regime versus the acidic regime. And so where proton coupling should occur, the system actually becomes entirely irreversible at some points of time scale, and then gets back a little bit of reversibility. And the idea with respect to now, we don't have a square scheme, but we have an L-type scheme. And the question basically becomes, how rapidly are we sampling the redox reaction compared to the proton transfer reaction, sort of the key point. And through the complete monitoring of the entire trumpet plot, you can see that this type of skewing results. And so where we're in that alkaline regime, things behave just like a redox reaction, basically, for the wild-type system. And when with the, particularly with respect to the mutant, it becomes less, the behavior of the wild-type system is abrogated, is relieved, but otherwise we have these regimes in between where we're decoupled, where basically we can't move protons and the same time scale as the electron transfers are occurring. Okay. So with those non-turnover examples aside, I do want to say a little bit more about some of these practical details and how we actually do these kind of experiments, which I realize is maybe the 1 10-minute chunk of time that most of you care about. So first, you need an electrochemical cell. I mean, you have to have an electrochemical cell that you're going to have a working electrode at that can come in various designs. You can make up your own design. You'll see the design that we use in our lab routinely upstairs. The one point that is worth noting is with respect to this cell and some of the experiments that I've described thus far, if we're going to be changing the potential rapidly, so if we want to do these fast scan experiments, an additional complication comes in the form of what's referred to as IR drop. And that's to say that we imagine that always there will be a resistive component within our electrochemical cell, and that we can control and we want to minimize. We want the resistance internal of the cell to be as small as possible, such that the electrochemical response, the capacitative charging and discharging of the electrode, does not have a strong resistive component as well, which basically means if you have too much resistance, then your ability to go to faster scan rates becomes bollocks, basically. You just can't do it. That you can't move the potential back and forth rapidly enough without encountering the inability of the cell solution to move charge, because it's just too big of an internal resistor. So one way to try to address that is basically through the physical positioning. That's what's trying to be illustrated here, thinking about the working electrode, auxiliary electrode in a three-electrode electrochemical cell as effectively being a resistor. And we want to minimize that resistance as much as possible with respect to the reference electrode. So the exact positioning to do fast scan work of these finicky bits of exactly how you're going to physically manage the overall volume of material that you are electrochemically interrogating becomes a potential issue. And so the idea of the cell configuration that we typically makes use of a so-called Lugin capillary. And so this Lugin capillary basically allows for the reference electrode to be in contact with the cell and to hopefully be positionable with respect to the auxiliary electrode and working electrode to minimize that sense of the resistive element that could give rise to so-called IR drop. But what about the working electrode? So with respect to the working electrode, again, there are many different parameters that one can that one can optimize or change, including the actual shape of those electrodes, whether we're using a simple disc or other types of physical configurations. These would all, once again, typically be macro-sized electrodes, meaning that they're on the sort of length scale of, let's say if it's a disc, say 1 millimeter in diameter. We have a different choice of electromaterials. If we're going to use gold, what kind of gold? Is it polycrystalline gold, like we typically buy of high purity wire? Is it vapor deposited into a specific shape, such that might be part of a fuel cell component? Is it somehow going to be annealed in some way or chemically treated? And then if it's bare gold, that's bare gold, and otherwise, presumably, it's going to be adsorbed with some type of thiol moiety. ITO and ATO are increasingly popular optically transparent semiconductor materials, where there's I don't have slides on this, but there are a few papers in increasing literature trying to generate macro, sort of meso-sized porosity within those surfaces such that metalloproteins or large macromolecules can find a happy conductive home. It has the added benefit of being optically transparent, so directly coupled to different spectroscopies. Whereas really the majority of the protein electrochemistry work that is, I would say, modern and involving electrocatalysis involves carbon-based electrodes. And so again, the nature of that carbon, where it comes from, what batch it comes from, who manufactured it, did you manufacture it? These are all variables that are come into play, and how those are configured then and further modified, as I'll discuss, are all aspects of a given experiment to be changed. So with respect to using gold, again, the idea of having alkane thiol-based modification, I've already addressed to some extent. We can think with a limited scope of what's available, sort of on the end, and whether or not you really want to use an alkane thiol versus aryl thiols or other types of so-called wires that might exist for faster electron transfer from the macroscopic electrode to whatever the adsorbed species is. This idea of separation or phase separation might be potentially of interest to you. And so some, again, old white-sized literature does demonstrate that if you have too big of a discrepancy between the scale of these alkane thiols, that you will have effectively islanding. You will really have phase separation occur at the electrode, whereas there's a tendency, if you think about a metalloprotein, it has a rough surface, it has a mixed surface in terms of having hydrophobic patches and different ionizable residues, and so having a mixture of species adsorbed on the gold electrode becomes very attractive. And yet, if you make that mixture inappropriately, what you might really have is effectively an island or a poorly mixed, poorly resolved surface, which may be good or may not be good for the particular mixture, for the particular system that you are investigating. There have been increasing desires to have physically attached electrodes. And so in the world of hydrogenase literature, Olaf Rödinger and Victor DeLacy and Anna and Thomas Moore at the Arizona State University have devised recently some different strategies for attaching onto gold, covalently attaching hydrogenase to try to give rise to an increased stability for long-term usage and the ability to actually visualize the displacement of those molecules on the actual surface to figure out what real surface coverages look like. The same sort of way people have utilized different ideas, and I just wanted to sort of rapidly step through a few approaches that people have used for coming up with other molecules to address on different kinds of gold surfaces. So trying to examine a protein that could be a biofuel cell component, like an oxygen-reducing cathode material. People have turned to lactases, where lactases have a tendency to bind hydrophobic substrates that they like to chew on. And so anthracene-decorated gold has become a potential tool in that regard, where you have to, you cannot buy this, you have to chemically make this, but either anthracene or pyrene-based so-called molecular beacons are an approach that then give rise to these very robust, chemically robust, mechanically robust protein films that here you may not necessarily learn much about the shape of the catalytic voltammogram, nor are you necessarily observing the electron transfer associated with the blue copper center, with the copper centers associated with the lactase in this case, but you definitely have electroactive current that can last. And then additionally, people have made use of aryl diazonium salts, and I'll discuss this chemistry a little bit more, as a means to reductively place in situ a moiety that can then be further chemically functionalized, and this has been done on both gold and on carbon-based materials. And so with respect to these carbon-based materials, again, sort of the highlight message that I like to give people is that really every protein is different, and that there is no sort of recipe for how you do this work. I mean, it really, the metaphor to crystallography and trying to grow protein crystals is maybe a bit belabored, but not much. I mean, a lot of what my students do when they're working in an electrochemistry project is try to figure out how to get the experiment to work at all, and then, the data analysis ensues. So with respect to thinking about just physiabsorption or chemiabsorption onto a so-called pyrolytic graphite edge, these sort of commonplace electrodes, people have examined various so-called coadsorbate, these green triangles that get used in Fraser's cartoons all the time, where what those are varied things that include charged moieties that will be redox innocent. Some of the oldest that have been looked at were actually chromium complexes that will be kinetically inert but charged, and so give rise to some other molecule that you could address upon the surface. Things like polymyxin or polylysine or other ionic polymers or aminoglycosides like neomycin, tobramycin, other aminoglycosides of different descriptions, which are antibiotics, are also useful for chemically addressing some things onto surfaces. And Jim Rusling at UConn has widely made use of dimethyl didodecyl bromide, or DDAB, to generate a so-called polysurfactant film, which then traps multi-layers of things onto electrode surfaces in a rather non-specific way. And so this type of chart I've shared with you is now dated. I should update this. But I did this about 5 years ago, I think, right before the last time I gave this talk. And just as a way of sort of illustrating how different variables can either be real keys or real detriments in a way that is not sensible or not predictable to trying to generate good electrochemistry. And that variables can include things about the actual protein buffer itself. Its concentration might need to be very low in a sort of surprising way. Yeast cytochrome CCP does not work if it's too concentrated for reasons no one really understands. It seems to self-aggregate and will not expose the portion of the protein that needs to interact with carbon to get that to absorb well. Whereas in the case of PDO, we found that only the most concentrated protein works at all. Sometimes deposition occurs with either rotation or with actually poisoning the electrode at a given pulse to give rise to a given potential, to give rise to the best electroactive films. Sometimes deposition occurs best only as a function of time. So in the case of azurin, it seems to be best behave on carbon if you incubate it for hours at 4C or at least several minutes at 30C. And if you try to absorb it instantaneously, it just doesn't absorb that well. So there's clearly some type of timeline barrier. And some other proteins, like we've mentioned cytochrome C554, if we utilize coadsorbates, it actually doesn't work at all. But without coadsorbates, it works quite nicely on graphite as well as on gold. So there are clearly some specific interactions that you can either enhance or disrupt through the usage of these coadsorbate type of molecules. And a sort of take-home point, and I would say for those of you that have been asleep, wake up now. The one thing that I'd like to leave you with is that everything can modulate the potential. Everything can modulate the potential. So when people say, the potential is, that's bullshit. You don't listen to that, because there is no the potential. I mean, it's very, very unusual to have a metalloprotein where the potential isn't modulated by temperature, by the nature of the ionic composition of the buffer. This is an example, of looking at those simple monoheme cytochrome Cs as a function of phosphate concentration that determines the ionic strength. And hydrogenobacter thermophilum behaves differently from Nitrosomonas europaea in an independent way, and in a way that gives rise to, again, differences of potential of tens of millivolts, and those tens of millivolts matter, at least in our world. And then as well, coadsorbates, in some cases, have been found to directly monitor the potential in a way that would not necessarily be predicted, though not necessarily published in terms of actual data. That's certainly been the case. And then while graphite has been great for many scenarios, it's not really great for all scenarios. And so this, again, is work originally from Judy Hurst's laboratory, looking at a couple different cytochrome Cs that have methionine ligation, particularly from Arabidopsis and another plant species. And they found that there would be this low potential signal that would result, so-called unidentifiable signal, in their 2007 JAX paper. This is work that then we have followed up with to demonstrate that all His-Met ligated cytochromes will give rise to this low potential feature to some extent in our hands. Every His-Met ligated cytochrome will give rise to both the sort of neutral or normal form that we would think of, and then a form where this is at least partially unfolded directly on a graphite-based electrode, but not on a gold-based electrode. And this, again, is sort of turning lemons into lemonade. It was an opportunity to examine how that behavior alters reversibly, and it is perfectly reversible as a function of temperature. You heat the thing up, it more partially unfolds. You cool it down, it behaves more like the normal form, which means that you can directly get out the redox thermodynamics associated with entropy and enthalpy associated with the redox processes of these two different states, which is great. And it means that we could even monitor those population sizes to tell us about what the actual equilibrium constant is for that kind of transformation. So with respect to chemically addressing electromaterials, again, even on graphite, grafting is possible. So graphite came in to being interesting as an electromaterial because it was thought to be so inert, and now people are trying to do everything they can to chemically address it, ironically. And so original work from Savient demonstrating that a series of different diazonium salts, aryl diazonium salts, including nitro diazonium salt, was able to be, again, chemically grafted onto an electrode surface. And the idea of this nitro-bearing moiety is that then that could further spontaneously be chemically reduced to an amine functionality, which is very hard to otherwise chemically address onto gold. And then that opens up the door to either carbodiamide-based coupling or using epichlorohydrin as another reagent to place an epoxide moiety onto the gold surface. And then as well, Carol Baffert and the CNRS group published a very nice paper in analytical chemistry demonstrating the use of what would be molecule 6 here, the carboxy functionality, to again chemically address hydrogenases onto graphite electrodes through that functionality. And further demonstrated that the difference from that paper shown between the top panel and the bottom panel is when you basically try to utilize the carboxy moiety for addressing what would be basic residues, lysine typically residues, on the protein surface through EDC-type coupling versus two different hydrogenases utilizing the nitro to amine functionality as a means of addressing carboxylic acid-based residues. And so they're both very chemically robust, but clearly the amount of current that you get out is much higher when you utilize the former of those two methods. So this allows for some sense of site-specific, it's not necessarily unimolecular site-specific, but some sense of site-specific chemical addressing of carbon. There are many other approaches that people are trying to develop in this world, as well in terms of the use of nanotubes that can be functionalized with pyrines and anthracenes, and then further docked with lactase-type molecules, and that's work from Shelley Mentier's laboratory recently in electrochemistry communications. And with that, I will say just a few words then in terms of the last major portion of the talk, in terms of this idea of electroanalysis and how we could try to understand more about enzyme function when we actually have chemistry at work. So in the case of now having a catalytic system, the type of the type of electrochemical cell design that we'll make use of upstairs is shown for you here. And so again, we have a working electrode where we have our protein-based film, a counter electrode that will be a wire, and some place for us to be able to get substrate into this system, and making use, in the case of an enzyme, of having a rotating disk electrode, or RRD. And when we're in that regime, we can imagine now having our immobilized reaction from before, in the presence of substrate, if this were a reduction reaction, can give rise to our negative current as current flows out from the electrode, reducing substrate into product. So that will occur with an overall rate constant that we're going to call K2 for the sake of our discussion right now. And the idea is that with respect to, again, if you're a biochemist, how is this useful to you? Well, it's useful to you because basically we can then treat that limiting current, which I glossed over very briefly. The idea of this limiting current is really as a velocity that now has a potential dependence associated with it and is linked, resulting from some electrocatalytic signature that is interesting, that is of interest to us as additional information. But even if you didn't care about any of that, you could still make use of that limiting current as a means to tell you about a velocity and very rapidly assess Michaelis-Menten-like behavior or not. However, there are a lot of complications that might come from that kind of work. And some of that work has to do, again, with the time scale associated with the experiment, as well as this ability to address mass transport control. I'll say a little bit about that, and this idea of actual film loss or potential time-dependent processes that are not involved in the chemistry that you care about. And so this figure illustrates for you this notion of what would happen if we have the same catalytic system, and you can imagine having your favorite enzyme, whatever your favorite enzyme is, that is a redox enzyme, because I'm sure we all care about redox enzymes, but at least I do. If you have that favorite redox enzyme absorbed on an electrode, if you change the time scale, the scan rate associated with the voltammetry experiment, this illustrates how we could be at slow time scale, slow scan rates, where we're allowing the enzyme to do its job, and it is working as fast as it can, and so we can generate these nice sigmoidal currents indicating catalysis. And as we increase the time scale of the experiment, scanning faster and faster, eventually we can outrun catalysis. We can swap the potential faster than the enzyme can work, and so now we read out again something that would look like some redox process that is occurring, maybe one of the redox cofactors that links the active site, or maybe a redox cofactor that is in the active site itself. So this idea of timescale means that when we're thinking about electrochemical experiments that are electrocatalytic, typically we're using scan rates that are going to be 2 millivolts per second, 5 millivolts per second, 10 millivolts per second, and not those values in volts per second, 1,000 times slower. Fundamentally, enzymes give rise to interesting, different shapes in terms of voltammograms. Whether we think of fumarate reductase, DMSO reductase, different or the same hydrogenases that have been treated in different ways, part of what we do is try to understand the shape of these voltammograms in a quantitative way, not just as an indicator of activity, but what these different bumps and wiggles are telling us about. And so with respect to those sort of bumps and wiggles, and this is where in the last 5 minutes I'll step through these different scenarios, there are different components that can give rise to the control, the determination of the shape of those voltammograms. And they include things like mass transport, interfacial electron transfer, whether or not we have slow binding or specific binding to specific redox states, whether or not we are a reversible enzyme or an irreversible catalyst of some kind, and whether or not there are actual electron transfer limitations in terms of proteins or even within a given protein. So with respect to the idea of reversible redox reactions, again, now rather dated work, but still quite impressive from Christophe Leger when he was a postdoc in Fraser's lab many years ago now, looked at succinate dehydrogenase fumarate reductase reactivity, demonstrating here in the presence of both the oxidizable and the reducible substrate, you can have this beautifully reversible wave at a potential that would be at zero over potential with respect to the actual fumarate succinate potential for these concentrations. This type of behavior is sometimes observable, but not always observable. But when it is observable, you can very nicely, again, make use of the actual limiting currents to recapitulate Michaelis-Menten type kinetics, and that is usually what is used by a protein electrochemist as a means to convince reviewers that the enzyme is okay at the electrode, because most people think that everything will unfold at the electrode, even though we've been publishing this kind of work for 20-odd years. Additionally, you'll notice that the potential associated with catalysis is changing, again, because it is linked to the binding of substrate as we're titrating in our substrate, in this case looking at oxidation. And so that type of titration means that you can extract out PKs, if you will, or the ligand binding constants associated with either oxidized or reduced form. In the case of this flavin-based enzyme, it is even more complicated because there are components that are one electron redox species associated with the oxidized, intermediate, and fully reduced form. If you don't want to engage in that full voltammetric work, it's also chronoamperometry has been quite useful from the standpoint of looking at something, in this case, of a nitrate reductase activity, where you can just think, in an ideal world, of just rapidly injecting in these different values, different concentrations of nitrate, and at a set value of potential, new values of reductive current are generated, such that you can very rapidly, on the time scale of 150 milliseconds, generate your nice Michaelis-Menten type behavior instead of a potentially arduous assay that is oxygen sensitive. In the case of challenges, we can think in terms of mass transport control as being a potential challenge. We need to rotate the electrode, and for some enzymes that are very, very fast, that is actually a potential limitation. And so the first paper on allochromation venosum, nickel iron hydrogenase, shows very nicely that basically this enzyme is working as fast as it can, and we can't get substrate into it rapidly enough. So this is looking at hydrogen oxidation, and that there's a Kutecky-Levitch relationship, that's what's shown for you here, on the basis of what the absolute rate should be if we could rotate the electrode infinitely fast to draw up substrate infinitely fast. So hopefully, if you're studying an enzyme that you care about, you are not under this limitation, but instead that the enzyme is so-called, the enzyme is in control and not mass transport. But with respect to more complicated enzymes that give rise to complexity in these so-called wave shapes, sometimes that complexity, whether or not we see diminishment of activity or enhancement of activity, actually depends upon substrate conditions, substrate concentrations. In the case of nitrate reductase, that's a respiratory enzyme. In the case of a different nitrate reductase, This has been well ascribed, again, in the work from Christoph's laboratory, in terms of an understanding of how the binding of substrate occurs differentially as a function of redox poise. In some ways, that the strange depletion behavior can be perfectly modeled on the basis of a, relatively speaking, simple model, but we still have different ability to bind substrates at different oxidation states. With respect to, again, further challenges, the type of behavior that's shown for you here, again, for a hydrogenase, indicates the ability of having an enzyme that's turning on and then turning off on the time scale of a given experiment. We build up an activity and it starts to decay, and then as we come back, depending upon the temperature, it will actually come back once again in a fully reversible way. This type of analysis, so-called activation, inactivation behavior, I'm obviously both running out of time and I'm not even going to dare to get into. It's one of the places where chronoamperometry has been incredibly useful. And Pierre, in my group, will be giving a talk on Friday that in part makes use of chronoamperometry as a tool to try to address these kind of mechanistic issues. And so one of the final challenges I'll tell you about is this idea of, again, having potential limitations of intraprotein electron transfer. That is to say, a lot of what I've suggested to you is that we always want to learn about the active site. That's what we care about. We want to understand about its chemistry. Many redox enzymes, of course, have that active site as a buried component, and there is another cofactor that provides a relay of electrons into and out of that active site. And in the case of an enzyme like sulfite reductase has a molybdenum cofactor in one domain and a heme cofactor in another domain. And the electrochemical response of that is dominated by the heme cofactor. And this is known, long time known from the first structure by Carolyn Kisker when she was in Doug Reese's laboratory. Has a flexible linker between those two domains such that a conformation can exist where that molybdenum is not in close electrical communication with the iron of the heme domain, but must be able to adopt a conformation where those can interact with one another. And the key point from this analysis is that we see just a single redox cofactor where that is the heme itself, and the heme domain only, and yet the enzyme will turn over. It will oxidize sulfite in this case, and will do so quite nicely, but in a way that is mediated fundamentally by that cofactor. So again, and I'm very sorry about the level of pixelation here, but the idea being is that that Christophe Leger, again, has constructed a very beautiful relay-based model that allows for one to quantitatively extract out information about the nature of that relay, and given that demonstrated as well that the actual potential that will be observed depends upon the nature of the relative rates of catalysis versus the intra-protein electron transfer. And so the sense of relaying, again, might be thought of as a detriment, but really has turned into a beautiful thing to examine in terms of protein-protein interactions as well. Cytochrome C and cytochrome C oxidase, Schwanella multiheme cytochromes have been addressed in this way, and my student Leon will have a poster on the use of ferredoxins and the so-called O4 family member as utilizing this ability to have relaying electron transfer be the principle by which we can still generate activity and examine different electrochemical signatures. So I'm not going to say anything about potentiometry given the time. I'll be more than happy to disparage that to you over beer. But I do want to remind you once again, if you're taking the tutorials, to please download QSOAS either directly from the website or from our Dropbox folder. And I've left some references for you, and I'd be happy to address any questions that you might have at this time. Any questions? You could be beaten down. So
have you ever looked at an isotope effect?
So no. I'm going to say very, very briefly, no.
Okay.
But we can discuss a little more detail. There are a couple people I know that have tried, and they have not been big enough to be observable.
By electrochemistry.
Yeah. But I think it's just the wrong system. Like you want to use.
So what are the constraints on,
I think the main
the sensitivity? You can't say an isotope effect of 2, or
I don't think so. I'd have to look up when it's the sort of thing where it's in thesis results and not in published paper results. But there's a question over there. Yeah.
I was going to ask, so when you showed heme structures, you showed them for cytochrome C, which has a C-type heme.
Mm-hmm. Yeah.
Do you know if anyone's ever done any ITC with heme type B?
Well, we're not doing ITC, but yes, I know what you're saying, and the answer is yes. So So it does turn out that C-type hemes have worked very nicely thus far. There are a few reports where people have examined electrochemistry of B-type hemes. Yeah, definitely. I mean, it's harder. I would say as people have tried to do that, largely speaking, used graphite again. And graphite does have a great hydrophobic character to it, like a B-type heme. So quite frequently, you can see in those old papers that there is undoubtedly adsorbed B heme, just free protoporphyrin 9, on the same electrode at the same time.
Okay.
Yeah.
Can you explain the term overpotential? I mean, how important it is in
Can I explain what? I'm sorry?
the term overpotential?
The term overpotential?
Yeah.
Well, so the overpotential is formally the potential with which something should occur with respect to the thermodynamic redox reaction if we're thinking about a catalytic event.
Okay, and how important is it in case of protein electrochemistry?
Well, so it turns out that many protein catalysts, many enzymes, tend to have very low, or essentially zero. This is sort of a world where the molecular people will say protein electrochemistry, like hydrogenases, have very low overpotentials, almost zero. But if you actually look in the paper, it's zero. So I don't quite understand that divergence. But so I think what is interesting are some cases where you do see that there is a shift from what the thermodynamic potential is, and that is usually due to some of these other cofactor-based challenges, interprotein challenges that I was alluding to at the end.
Okay.
So sometimes I would say in our hands, if we see an overpotential that's at work, that's usually where there's something interesting happening to be understood.
Thank you.
Are there any other questions? Well, if not, let's thank Sean.